Hi everyone, my name is Darya and I'll be presenting our work Myco, Unlocking Polylogarithmic Accesses and Metadata-Private Messaging. This is joint work with Deevashwer, Rathee, Bhargav, Annem, and Raluca Popa. So why do we need to hide metadata? Well, suppose we have a user, Alice, communicating with a user, Bob, over an end-to-end encrypted messaging app. The good news is that these apps conceal message content from attackers. So what's the problem? Well, suppose you have an adversary like Eve. The problem is that Eve can see who communicates with whom, when, and how many messages they exchange. And while this might seem like benign information, it can have real consequences. It turns out that the NSA can derive 25,000 people's networks given just one person's call metadata, and tweet metadata alone identifies users with 96.7% accuracy. And so it's no surprise that Stuart Baker, former NSA General Counsel, says metadata absolutely tells you everything about somebody's life. If you have enough metadata, you don't really need content. And according to General Michael Hayden, former NSA and CIA director, we kill people based on metadata. Fortunately, a large class of prior works come together in what I like to call the trilemma, trying to solve this problem. Some works have cryptographic privacy of the metadata. Other works have asynchrony, which means that clients can go temporarily offline without losing access to their messages. Other works have near linear server overhead in the number of users n when handling everyone's queries. Traditional mixed nets fall into near linear server overhead. DC networks have cryptographic privacy. Flexible mixed nets and trusted hardware-based solutions have near linear server overhead and asynchrony, but lacked cryptographic privacy. Cryptographic mixed nets have near linear server overhead and cryptographic privacy, but no asynchrony. And PIR, or private information retrieval-based systems, have cryptographic privacy and asynchrony, but not the efficiency. So the question we ask in this work is whether any work can achieve all three. I want to start off by zooming into private information retrieval, which is a cryptographic primitive where Alice can query a database at index I without revealing I to the servers. So as you can see here, Alice can take the element I, and even if it's the case that the server is compromised by Eve, she cannot see which index Alice queried. Messaging systems based on PIR have a couple of great properties. They have cryptographic privacy for message confidentiality, integrity, and metadata privacy. They have asynchrony, which means clients can go temporarily offline without losing access to their messages. But the problem is that the server overhead is quadratic in the number of system users n, resulting in poor throughput. In Myco, we want to adopt these first two properties, but we're also able to achieve a server overhead that is asymptotically better. In particular, it's n log squared n, resulting in at least 302x the throughput of PIR-based works. And so we believe that we've solved the trilemma. Moving on to our system setup, Myco consists of two servers and n clients, and each conversation consists of a sender, Alice, and a receiver, Bob. Each person can have up to q contacts, and each conversation is going to have a shared symmetric key k. Each party tracks the current epoch, which are discrete time intervals, and to resist traffic analysis, clients send cover traffic in each epoch. PIR-based systems have a very similar setup. So most solutions are multi-server with a non-collusion assumption, and some works are single server, which has a stronger threat model at the expense of performance. A subset of these overall works support the general purpose messaging setting, which we will also target. Moving on to our threat model and security guarantees, we assume that any subset of clients and up to one server may be maliciously corrupted. Clients can go offline as long as their online patterns are independent of communication. And for availability, we assume that the servers do not deny service. We have message privacy and integrity. So we have end-to-end encryption and tamper detection by receivers. And we have metadata privacy. So adversaries cannot link senders to receivers. And we prove the security of Myco in the simulation-based security paradigm, which captures denial of service attacks. Moving on to our protocol, I want to start off by describing how PIR operates in the distributed trust model, which is symmetrically. The idea is that Alice is going to derive from the shared secret K a message location L, and she's going to symmetrically write her message to location L in each of the servers. At which point Bob is also going to derive L from the key K, and he's going to do a symmetric PIR read at location L in order to obtain the message. This is a linear scan over the database, which results in a quadratic overhead for end users. In order to avoid this cost, we introduce asymmetric distributed trust. Our insight is that we can leverage the distributed trust servers asymmetrically to unlink reads and writes. The idea is that Alice is going to write to server 1, messages are going to get transferred over to server 2, from which Bob can go ahead and read. And this achieves linear server overhead for end users. Even if it is the case that server 1 is compromised, Eve is going to conclude she doesn't know who read the message. And if server 2 is the one that's compromised, she's not going to know who wrote the message. So how can we actually organize our messages within the buckets here? In prior work, in particular in Tolic, if it is the case that bucket L was full, then Alice is going to write her message to a backup bucket L prime. And if it is the case that L prime is also full, then she's going to have to evict a message from one of the buckets, and that's where she's going to write her message. So in PIR-based systems, message placement depends on other message locations. And this is completely okay in PIR because PIR's linear scan hides read access patterns. And so our first challenge is to avoid this costly linear scan while hiding access patterns. So what happens if we just use this dependent bucket assignment for Myco? Well, we would transfer over the messages as they were written over to server 2. But the problem is that suppose Eve actually was the person who wrote the evicted message and is trying to read it now. She's going to conclude, hey, I found my message in bucket L prime prime, so Alice wrote to bucket L prime. The problem is that dependent bucket assignment leaks honest user behavior. In order to avoid this, we introduce independent bucket assignment. Recall we want Alice to write her message to server 1, and we want it to get transferred over to server 2 for Bob to read. Our idea is that messages should be written to locations independently of other messages. We realize this by first introducing this magical world where we have infinitely sized buckets. And of course, this is not realistic, and we have to cap the bucket somewhere. And so to do that safely and efficiently, we introduce unbiasable writes. Let's zoom into one bucket to see how this works. The idea is that we set the bucket capacity large enough to fit all assigned messages to that bucket. So even if we have 1, 2, 3, or 12 messages assigned to bucket L, everything should fit. Next, server 1 is going to fill each bucket with dummies and then shuffle it before sending it over to server 2. If it is the case that one of those messages belong to Eve, she's going to find her message at a random position in bucket L, and so she can't learn anything about Alice. But of course, we can't have these infinite buckets, and that's where we run into a problem of biasable writes. Eve can actually craft a malicious location L. If she owns 8 clients, they can all write to that same bucket, and so Eve can distort the message distribution to overflow bucket L. And we would actually need linear size buckets to prevent this overflow. To solve this, we introduce unbiasable writes. So recall this bucket belongs in server 1. Eve, for simplicity, is going to have 2 malicious clients. The first one is actually going to have not L, but a similar intermediary message location that we'll call F. And it's going to send this over to server 1. Server 1 is going to have a server routing key, KSRK, which is going to use to apply a PRF on F salted with a unique client username in order to produce the location L that the message is going to end up in. Here's what happens with the second message. It's also going to have that location F submitted, but because we have this PRF layer happening at the server, it's not going to be the case that L is equal to L prime. In fact, L will very likely not be equal to L prime, and so Eve can no longer clog the buckets. And we also prove in our paper that logarithmically sized buckets in N should suffice. Great, so how do all of these different buckets come together? Well, we have an epoch-based system. So each table is going to need N buckets, and messages are going to expire after an expiration period of delta epochs. So the oldest hash table is going to go ahead and expire in every single epoch. The tables are going to rotate. The new one is going to get written to server 1, and it's going to get transferred over to server 2 in the protocol. And we call the system matrix Myco. Alice is going to write to that new hash table. It's going to get transferred over to server 2, and Bob's going to read the message. Each server stores a matrix of N times delta buckets, hence the name. So this all seems great, but the problem is that what if Bob goes offline? In particular, what if he goes offline for delta equals 5 epochs and he's in 2 conversations? The problem is that when he comes back, he's going to have to download Q times delta buckets to avoid missing a message and to remain oblivious. And this has a significant amount of total work because it turns out that constants do count. So it's clear that we require a stronger primitive to obliviously fetch across both epochs and conversations. So it's back to the drawing board. We're looking for something with oblivious accesses, and we're looking for something with sublinear accesses. So the natural question is, what about ORAM? In particular, say PathORM. So for some background on PathORM, we have a server and a client, and the server is going to have a database that's situated as a binary tree. The client is going to have a position map that stores assignments and a stash for overflown blocks. So here is our assignment as shown in the position map to location L, which means that along the route to the leaf node L, that message should be in the tree. Next, we want to access this message, which means the client is going to read the path. And next, it's going to have the message be assigned randomly to another location L prime. And next, we're going to push every block to the deepest non-full bucket that intersects with the old path. So the bolded nodes here are the new path L prime, which means here is our least common ancestor node as so. And if it is the case that both of these bolded and orange nodes were full, the message would go to the stash. Next, we're going to write back the path, re-encrypted with fresh randomness, over to server 2, and this is how a PathORM access works. If it is the case that the server is compromised, all it sees is that a random path is downloaded and written back, which hides access patterns. And also the paths are of logarithmic length, which is great for efficiency. So what happens if we just want to use PathORM for Myco? Unfortunately, prior work has discounted using it because of the fact that we have this trusted client that stores all this sensitive data, like the encryption key and the position map. So if it is the case that we want to use PathORM, the crucial question is, who should be our ORAM client? The natural question is, can it be the client? The problem is that if one of the clients are malicious, a single malicious client could compromise honest client message locations with that sensitive data. The next question is, can it be server 1 in our distributed trust model? So let's give this a shot. We'll put the position map in server 1, and we'll have server 2 be our ORAM server with the tree. Alice is going to write her message to server 1. It's going to get transferred over to server 2, and then Bob is going to go ahead and read the path. Next, he's going to have to write back that path through server 1 because, again, server 1 is our client. But that's an issue because if server 1 is malicious, it could link the reads to the writes because it saw both the write and the read as the client. So this clearly won't work. The way we solve this is through what we call a read static messaging tree. The insight is that due to the inherent access pattern of messaging, we don't actually need to reassign messages through server 1 at all. In other words, Bob doesn't need to write back a message. He just needs to read it once from Alice. So what we're going to do is we're going to have this message location input F like before. Alice is going to write F and the message to server 1. Server 1 is going to use that server routing key to help derive the message location L. It's going to get written to L in the position map. It's going to get written over to the tree. And next, the server routing key gets transferred to server 2. When Bob wants to read, he has to download that key. He uses F, which he locally computes to derive L. He's going to download the path to L, and he successfully obtains the message. And so read and writes are successfully decoupled through our read static messaging tree. If it is the case that server 2 is malicious, it could still link reads to writes if we're not careful about how we actually do the write to server 2. So the question is, how can server 1 write to path P of L of server 2 without disclosing L to server 2? The way we solve this is through oblivious batch evictions. So the idea is that we can actually leverage the high volume of writes that are inherent to a messaging system in order to process writes in batches. So first, server 1 is going to be able to read the randomly sampled path set of the tree that you can see here in orange. In particular, say that the number of users in this case is n equals 2. We have 2 paths in our path set that are sampled by server 1. Alice is going to submit a message as well as a message location input over to server 1, who's then going to, again, use its server routing key KSRK to derive the message location L. Here, you can see the message location L, and the message is actually going to get written to exactly the least common ancestor node of the path set and the intended path, very similar to PathORM, with one difference. It has to be exactly the LCA, because recall from earlier that if we wrote anywhere but the LCA, we would violate this independent bucket assignment requirement of our system. Next, the path set is going to get sent over to server 2, at which point we're going to also send over KSRK. To read, Bob's going to download KSRK like before. He's going to compute F, he's going to derive L, and he's going to download the path, at which point he can obtain his message. And we're done with describing oblivious batch evictions. Also, Tree Myco has these nice percolation properties. So say the message went to this particular location in the first epoch of the system. In the next epoch, say that we have this blue path set. Notice that the message does not move because there's no deeper least common ancestor on the intended path. But in the next epoch, suppose that purple is our path set. You can see that the message goes very deep because it is the case that the path set and the intended path have high intersections. So as new path sets are selected per epoch, messages are going to percolate towards leaves quite effectively. And this also leaves space for new messages. Also, server 1 is going to go ahead and delete expired messages that are older than delta epochs in each path set, which is also great for freeing up more space. From a theoretical perspective, path sets consist of n paths, so messages never clog up buckets near the root. In particular, we proved that in the beginning, we're going to have all of the messages fall under a particular location D0. In the next epoch, we show that there is some D1 greater than or equal to D0, where all of the messages from that first epoch are going to fall under that line, and the new messages are going to go under D0. In epoch 2, you'll notice that the original messages will go under D2, the others will go under D1, and we'll have the new ones fall under that same original D0. Suppose that now is the expiration duration. So what's going to happen is that these first written messages are going to expire. Next, we'll have the blue messages under D2, the pink messages under D1, and new orange messages under that same original D0. We prove that the bucket size we need in this case is log of n delta cubed, where delta is the expiration period and n is the number of users in the system. And another nice property of this is because we proved that we never have the buckets near the root get clogged, there's no need for a stash at all in tree Myco. So tree Myco and matrix Myco have some pros and cons to them. In particular, for tree Myco, we have sublinear accesses due to reading a logarithmic length path of the database per read. And in matrix Myco, we also succeed with sublinear accesses due to reading a potentially large but still constant number of buckets. For tree Myco, we have cross-epoch obliviousness, which means clients do not need to read from all epochs and conversations. And matrix Myco struggles here. We have this high overhead since we read Q times delta buckets to avoid missing messages and to remain oblivious. But tree Myco isn't perfect either. In particular, receivers must guess which path to download per query because we can't re-query things. And in the case of matrix Myco, receivers actually download all possible message locations, eliminating the guesswork that exists with tree Myco. So the question is, can we get the best of both worlds? And we answer this question in the affirmative. Our idea is to use matrix Myco for notifications and tree Myco for actual messages. So on the top here, you're going to see the message tree Myco, and on the bottom, you'll see the notification matrix Myco. So first, notice that our notification can just be a simple lambda bit notification, which is going to take away that high overhead that we experienced from the constants before. We'll have this notification input fnotif, as well as the notification that gets transferred over to server 1 upon the right. Server 1 is going to help with computing this lnotif, this final notification location, at which point the notification is going to get written into the matrix Myco table. Now it's time for the message write. So server 1 is going to read the randomly sampled path set as before. Alice is going to take her message as well as her location F, and she's going to send that to server 1, who's going to help with deriving L. And you can see the intersection here. The message is going to get, like before, written to the LCA, and we're going to transfer over that notification table to server 2. We'll also transfer our path set to server 2 containing the message, as well as our server routing key. It's time to read, so Bob's going to download KSRK. Next, suppose that he's been offline for 2 epochs and he's in 2 conversations. So he's going to compute all of the potential locations that he could find a notification, and he's going to download all 4 of them, as so. He'll find the notification in a particular bucket, which is going to indicate to him, hey, Alice is the person that wrote to me, and she wrote to me at epoch T. Then Bob is going to use this information to figure out which path he needs to download from the messaging tree. So he's going to take F, he's going to use it to compute L, he's going to download the root to leaf path to L, and here is where he obtains his message. And we're done. This is the end-to-end technical details of Myco with notifications. Moving on to our implementation and evaluation, we evaluated Myco with an implementation that's 5,500 lines of Rust, and you can find the code base here. And here's the QR code for it. The question we asked is, how does Myco's performance compare to PIR-based metadata private messaging systems? So our baselines were Pung++, which took the single server system Pung and plugged in a state-of-the-art PIR scheme, CLPIR. And we took Talik++, which is the two-server state-of-the-art, and we plugged in a state-of-the-art PIR scheme, DPFs. We had our baseline and Myco servers deployed in GCP machines that were 64 vCPUs on US West 1, and our clients were GCP 16 vCPUs on US East 4. They're on opposite sides of the coast for realistic WAN latency. We also conducted an empirical capacity analysis because recall that we set our bucket capacity large enough to fit all assigned messages, and we want to have a bucket capacity that is quite efficient concretely. For matrix Myco, we found that a bucket capacity of 25 suffices to prevent overflow. And for tree Myco, we found that a bucket capacity of 50 suffices to prevent overflow. Here was our core finding. For throughput, we have 11 to 302x the throughput of Talik++, and we have 106 to 2219x over Pung++. And the reason for this significant improvement in throughput is really due to Myco's O of n log squared n server work as opposed to quadratic. You can see here on the left, with the linear scale, you can see a large gap overall. And this log base 2 scale on the right, you can see the degradation over time with the PIR-based schemes due to their linear accesses, in contrast to the fact that we have very little degradation, as you can see. Moving on to single client latency. So the idea here is that what if we lived in a world where just one client was online? So the thing with Myco is that even if only one user is online, server 1 must perform a batch write on n paths to ensure that our capacity analysis holds. And so you can see here that we have 50-some seconds for one particular epoch here with a single client online, whereas we're actually beat out here by Talik++ and Pung++. But again, this is an unrealistic scenario of a single client. So the worst case latency, where every single client is online, has an epoch duration of less than 2 minutes for Myco, while it's 8 hours for Talik++ and 60 hours for Pung++. Moving on to bandwidth, Talik++ has no server-to-server communication, but Myco sends 1 to 36 GB of data per epoch between the servers, but this only comes out to about 100 kilobytes per user, since we have to handle the work of all of the users. Talik++ has much lower client-to-server communication, but I'd like to highlight that all of the client-server communications grow sublinearly with n. Nonetheless, for future work, we'd like to improve our concrete communication costs. If you're interested in the namesake of our system, Myco stands for messaging your companions obliviously, and it's also inspired by mycorrhizal fungi, which plants use for sending anonymous signals through tree roots. Zooming out here, Myco leverages an asymmetric distributed trust setup, as well as a novel oblivious data structure to achieve 2 to 3 orders of magnitude throughput improvement over PIR-based works. And in doing so, we become the first practical metadata-private messaging system to solve the trilemma. For future work, we'd like to improve our concrete communication costs. Here is our paper, as well as our code. Here's where you can find me on the internet. Thank you.